If you think about what we've done so far this school year, we started as small as we could start. First, we just looked at matter in general. Characteristics of matter, what makes something matter, what makes something not matter. Remember, the not matter things is the stuff you'll focus on in physics. And then once we discovered everything that was matter, we went all the way down to the atom and learned everything there was to learn about the atom. After we looked at the atom as a whole, we started looking at parts of the atom. First, we went into the nucleus, protons and neutrons. All right, and that's where nuclear chemistry was. Then we moved outside of the nucleus, where all the electrons lived, and studied electron configurations. And then we took a look at the periodic table and just started looking at entire elements. And now we know where elements have, where they want to gain more electrons, where they want to lose more electrons, where the elements are larger than others. And now we're going to take what is really the next logical step. Now that you know pretty much everything about a given element, its protons, its neutrons, its electrons, a bunch of facts about them, we're going to start taking other elements and combining them together into compounds. Now, compounds was a vocab word in Unit 1. We talked about it's a type of pure substance. But remember, what I shouted at you when I first introduced compounds was it's any time you take two different squares and put them together into a bonded molecule or compound. Water was one of the examples of what we use. All right, we've got hydrogen atoms, oxygen atoms. That's a compound. The rest of this semester, the rest of November and all of December, we're going to be looking at 3 different types of bonds. And the bonds is simply the word that describes, well, if these two H's are going to join with this one oxygen to form water, how are they gripping each other? How are they staying together? That is what the word bond should make you think of anyway, right? Besides James Bond, right? Anybody? New movie came out this weekend. No one cares. Anyway, but we're looking at bonding is our next main focus. Now, we've got 3 main types of bonds. One of them we talk about very briefly. I'm going to knock it out the first 5 minutes of this lecture. It's metallic bonding. The second, you don't have to write yet, just listen. The second is ionic bonding, and it's the most important one in terms of this class. And the only reason I say that is the ionic bonding comes with a bunch of rules that we're going to learn tomorrow, that important Friday that you're not allowed to miss. And those rules are going to stick with you through every unit, almost every unit the rest of the year. We'll get to a point near the end of the year where it finally fades out. And then after Thanksgiving break, I'll introduce you to the third type of bonding, which is called covalent, which is also important and comes with rules, but ionic seems to be the heavier one. And that's where we're going to start tiptoeing in today. There'll be a video to support the answer to that question. If you take a look at your new cheat sheet, I'm going to knock out everything on the front side of it. But just to give you a little note, if you look on the back real quick, there's a section we won't be covering. As I told you, I'm cutting out a part of this unit. So I don't mark it out because we're going to come back to it after break. But I just want you to know that where it says acidic nomenclature and everything down, I will not be covering that before Thanksgiving. That won't be on your next test because we're doing things slightly differently than normal. But everything else we will eventually get to. Anyhow, go back to the front and let's start with what bonding is in general. Again, it's a bond whenever 2 elements come together to form something. All right, if we have a sodium and we have a chlorine, they each have their own square on the periodic table. All right, and when they're in their own squares, that's beautiful. But what we're focusing on is when they become this. What is that? Anybody know? I've asked you this before. So what was it? It's sodium and chlorine. What do we call it as its common name? So salt would be its common name. Sodium chloride is its chemical name. All right, but yeah, this is actually table salt is what I would say. But When the Na and the Cl joined together, it was because of electrons, and I'm going to show you exactly how. But it's because of the way that the electrons, the valence electrons, interact with each other. If I read off the cheat sheet, it says atoms are more stable when they're bonded together. So get this first thought into your brain. The whole reason that that guy and that guy will form this guy is because they want to become more stable. Remember, when we looked at our trends, the noble gases were the only ones that wouldn't let you touch their valence electrons because they already had their octet. They already had 8 in group 18. But all the other elements don't. So when these guys come together, they're going to move their electrons around so that the octet rule is satisfied for both of them. And I'm going to show you exactly what that looks like at the end of this lecture. But I want you to understand, the whole reason that these two elements, or any 2 or 3 or 10 elements, will decide they're going to bond together is because they want to become more stable, trying to get their octet. The first type of bond I want to talk about is metallic. In general chemistry, this survey course that you're taking right now, we talk about it very little, but it'll be on the test. The stuff, that section that you see on your cheat sheet, will certainly be covered. What's this? What was it? Aluminum. Let's just call it aluminum. You're right, it's foil. But let's just call it aluminum for the purpose of my periodic table. How would you describe this? This is a... y'all are trying to impress me. Yes, it's malleable. All right, because it is a... Yeah, it's a metal. This is absolutely a metal. All right, it's not a metalloid. It's the only element on that zigzag that's not a metalloid. But yeah, this is a full-blown metal. Inside this metal, all right, inside the aluminum, the parts that you can't see that are making it stay is one big piece. There's bonding going on between aluminum atoms. There's a picture here. I'm going to try to cheat and show my computer people. All right, but if you focus on that image, all of the silver balls that you see there are considered to be the atoms of the aluminum. You see the red things? What do y'all think the smaller red dots are? The smaller red dots are the electrons. And here's what happens in metallic bonding. The term that we have for it, and you can verify this sitting on your... Sorry, now I'm all messed up. I'm reading off of your cheat sheet now, but we call it a sea of electrons. What happens is if these are the aluminum atoms, all right, a bunch of aluminum atoms have to be together to make an aluminum this size, right? Aluminums are teeny tiny. So if I'm going to have an aluminum that you can see, there's going to be a bunch of aluminum atoms all joined to each other. And the way that the bonding works is that the electrons that the aluminum has are constantly bouncing around each other. Metallic bonding is really interesting because unlike the other bonds we'll look at, you can't really pinpoint the location that an electron will be because they're what we call delocalized. They're constantly swimming around all of the different aluminum atoms. So again, the atoms that are making this guy up right now, all of the teeny tiny atoms, the electrons that the aluminum atoms have are bouncing all over the place all the time. It's this fact, it's this sea of electrons that makes metals conduct heat and electricity. Because here's what happens. As the electrons are going crazy, they're going crazy all over those atoms. If heat or electricity is introduced to one of them, what does that one electron do once he grabs that heat or electricity? He runs somewhere else in the metal. He goes somewhere else. If he's right here and he gets hot, he then runs over here with it. And when he's moving around all of the different aluminum atoms, he's sharing that heat and that electric charge with all those other electrons, and they're still running all over the place. Metals conduct heat and electricity really well because of the way their electrons do this. The other two compounds, the other two bonds that we're going to talk almost about all the time, because you won't hear me talk about this very much, they don't work quite that way. Their electrons are more predictable in regards to where they are. It's the metallic bonds that have this sea of electrons where they're just swimming across all the aluminum or whatever metal. I'm out of breath. I'm just using aluminum as my example, all right? But they're swimming throughout the metal that the atoms are making up. And then the other stuff that's there is stuff that we've covered. They're malleable. You still need to know that. They're shiny. Metals are inherently shiny. They can get dull, but one of the general characteristics is that they're shiny. I'm going to break your phone into like 8 pieces and throw it at you. Thanks. Oh, that's on the video. I'm in so much trouble. Are there any questions over this general idea of metallic bonding? Again, reference your cheat sheet for the wordy version. What we'll be focusing more exclusively on is ionic bonding for this unit anyway. So let's take a look at what ionic bonding is. I need you to make sure that your periodic table looks like that. I had you do it once, and if you're using the same table, awesome. You don't need to do anything. But if your table does not have the oxidation states, the predicted charges, those are the same things, the black, then you need to add them big and bold and beautiful because they are your life for this unit. For my computer people, it's kind of hard to see. It looks like that. Got it? I'm reading off your cheat sheet. It says, an ionic compound is an attraction between cations and anions. An attraction between cations and anions. Have you heard the expression opposites attract? That's ionic. The idea is look, focus. This is the most important thing I say like all day long. To be an ionic compound, the two elements that we're going to join together, one of them will come from there. What charge will the guy be, will the element be if he comes from that side? Negative. He'll be an anion because the negative guys live to the right of the zigzag. If an ionic compound requires a cation and an anion, where will the other element in the compounds come from? The left side. So let me say this one more time. I'm sorry to say it so slowly, but it's one of the things that so many people never get. To be an ionic compound, it's so simple. There'll be two elements coming together. One of them will come from the right of the zigzag. The other one will come from the left. And that makes it ionic. So, with that in mind, if I give you calcium, and I say, I want to make calcium into an ionic compound. I want to join him with something to make him a compound. Somebody yell an element that could go in that blank. Fluorine. Ooh, fluorine would be good. Why is fluorine okay? Because he's got a negative charge. You see how one of them was positive and the other was negative? Ooh, look here, look here, look here, look here, look here. The positive always comes first. Some of y'all were already thinking that thought. The positive always comes first. All right? It's kind of like reading a book. If you look at the periodic table, if you read the book, what always comes first when you're looking at the table? The positives, right? If you go from left to right, it's positive then negative. All of these compounds will always be positive then negative. So, let's say that I had phosphorus. Ooh, phosphorus. And I say, I want phosphorus to be in an ionic compound. Somebody different. Shout out an element that I could put with them. Aluminum. Aluminum is a great answer. Here's why. If you missed it, here's why. Phosphorus has a predicted charge of -3. Do you see it? Do you see where I got the -3? Do you see it? Do you see it? Do you see it? Yeah. It's at the very top of his group. Aluminum has a charge of positive 3. And the fact that one is positive and one is negative is what makes it ionic. Yeah? This is the simplest definition of an ionic compound. You've got 2 elements, one's positive, one's negative. Easy, right? Different sides of the zigzag. Just say easy. Say it again, easy. God, this is easy. That's how you identify it as ionic. And then you can see there's a list of characteristics you need to know too. It says electrons are donated from one atom to another atom to form a weak neutral bond. These compounds are very weak. They're easily broken. Look here, look here. Here's what I want you to imagine. I want you to imagine that if I took aluminum phosphide here, if I took him off of the board and held him for you, I want you to imagine like a crystal structure, a very fragile crystal structure. What would happen if I threw it as hard as I could at Caitlin's face here? What would happen? Do you think it would hurt if I threw this crystal? If someone threw a crystal at your face, Roman, would it hurt? Yes, it would hurt. He said, no, it would break. You're right, it'd break right over your face. But it would break. He's got a good point. All right, here's my point. Look back here. This crystal structure, any ionic compound, it's hard. It's hard. If I go like this onto it, it would hurt my head. But when I did it, it would break. Because even though something might be really hard, if you imagine a glass cup, it's hard. Ding, ding, ding. But if I drop it, it'll shatter because it's very weak. That's the way that all of these ionic compounds are. All right? It's just an electrical attraction. All right? Think about magnets. When magnets stick together, you can then very easily pull them apart unless they're super industrial magnets. A lot of y'all already tried to poke a hole in my theory. All right? But think of it more generally. Magnets stick together because it's a plus and a minus. And you can easily break them apart. There's some other stuff there, high melting point and boiling point. These will be some facts that you'll want to be able to spit back out on a test, so make sure you monkey grapefruit the front of that. Just make flashcards on characteristics of ionic compounds. But here's the biggest gist of what you need to know. Are there any questions so far? Ooh, let's say I give you copper. Let's say I give you copper. Somebody tell me something I could bond with copper to make it an ionic compound. Will you quit using fluorine, you boring... Nitrogen. Nitrogen. Fluorine's a great answer. All right. Hey, which side would the nitrogen go on? Would it go in front of him or after him? After. All right. Now, for those of y'all that are like, no, wait, what? I don't get it. Nitrogen, if you look at his group, if you put your finger on nitrogen and go all the way up, you'll see a -3 written up there. For today, I don't care about that 3. The fact that he's negative. Copper is a transition metal, and all transition metals they're all positive. They're all cations. So positive, negative, ionic. So how do they bond? What do the electrons do when these guys actually come together? I want to show you. So in your notes, I hope you've been writing stuff I've said and examples I've written. But here's what we're going to do. I'm going to pick a cation and an anion. All right, I'm going to choose potassium, and I'm going to choose bromine. All right, so there they are, squares on the periodic table. And I'm going to join them together. Now, potassium has a positive charge. Bromine has a negative charge. Therefore, we're about to make an ionic compound, right? Say easy. God, it's easy. Now, here's what I'm going to do, though. I'm going to make over kind of in the margin of your notes, I'm going to use tally marks as I draw examples of the elements, because we're going to use valence electrons, because I want you to see what the electrons do when these guys decide that they're going to get hitched. Vegas style, yeah, they're eloping. So I'm going to first draw a potassium. There he is. All right, you're working with me. This is to the side. All right, and then here's where my work area. So draw a potassium. Now watch. I've drawn one potassium, right? There he is. How many valence electrons does potassium have? He's got one. Now, if you missed that last unit, here's how I know. The group numbers, 1 through 18, tell me the number of valence electrons the entire column has. Potassium is in column number 1, group 1, so he's got 1 valence electron. Draw it. There's his Lewis structure. All right. Now I'm going to draw a bromine. All right, there's bromine. So watch, I'm going to go to my tally marks. I have now drawn 1 bromine. How many valence electrons does bromine have? 7. He's got 7. Now again, look here. I don't want you. If you've missed last unit, you're behind. Bromine is in group 17, right? Everything in group 17, if you cover the 1, has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. 1 on each side before you double them up. Yes, sorry. I knew what it was going to look like. Hey, what are the 2 magic numbers for becoming stable? 8 and 0. Now 8's the number, right? 8's the octet. But we said that visually, 0's just as good. All right, it lets the element drop down to the lower energy level. Anyway, do you see what's going to happen here? Do you see what the electrons can do here to make one of the elements have a happy number and the other element have the other happy number? Do you see? During ionic bonding, electrons are donated from one atom to another. Listen to me say that again. Look here, look here. I know you're drawing because you're good little students, but look here. During an ionic compound, a plus and a minus getting together. One of the atoms donates electrons, while the other atom accepts electrons. The atom that's donating electrons is trying to get down to 0 because that makes them stable. And the atom that's receiving electrons is trying to get up to 8 because that makes them stable. So when this happens, let's see what they look like. Now you have a naked potassium. Once he gives that electron away, he's got 0. What does bromine look like now? He's got a full octet. Great way to say it. There's the 7 that he had, and then I moved this one over to him. So all I had to do was draw 1 potassium and 1 bromine, and I could make everybody happy by moving dots around. 0, 8. If I was going to write this formula, potassium bromide, it would just look like this, KBr. Because there would be 1 of each of them. 1 K and 1 Br. Now, a lot of this doesn't really have context for you yet, so let me show you one more example, and it's actually our last example of the day. I'm going to erase this. On your periodic table, I want you to find aluminum and nitrogen. I'm sorry, not nitrogen. Aluminum and oxygen. Aluminum and oxygen. Let's get their squares on the periodic table. Is aluminum a cation or an anion? A cation because he's got a positive charge. Is oxygen a cation or an anion? Because he's got a negative charge. Does anybody not see how I know that? All right, it's this here, that there, those black numbers. So it's going to be ionic because one's positive and one's negative. Now we're going to do the same thing, but you're going to see that this is a different experience. Over in the margin, I want to have tally marks for aluminum and tally marks for oxygen. As we try to make everything happy, we're going to move dots around. Everybody wants either no dots or 8 dots. All right, I'm going to draw an aluminum. How many valence electrons does aluminum always start with? He's got 3. Aluminum is in group 13, so he's got 3. I'm going to move this up a little bit because I need space. All right, so watch. I've drawn 1 aluminum, my little tally marks. All right, let me draw an oxygen. How many valence electrons does oxygen always start with? He's in group 16, so he's got 1, 2, 3, 4, 5, 6. Everybody with me so far? This is all last unit stuff. So watch, we need to move electrons around. Watch, do it with me, do it with me. I'm going to move this electron over there. All right? I've now got aluminum a little bit closer to 0, oxygen a little bit closer to 8. All right? It's ionic. We're donating electrons. I'm going to take this electron and move it right over to there. All right? I'm going to redraw my pictures now. Now that that's happened, after the red has happened, how many dots does aluminum have on him? He still has this guy, right? I was unable to move that electron. How many does oxygen have? Ooh, yeah, he's got a whole octet. All right? He had 6, but I moved 2 over. Is everybody happy now? Ooh, who's not happy? Aluminum's angry. Aluminum's actually a lot angrier than he was a moment ago, because remember, the closer you get to the octet, the more reactive you get. So we're not done. What could we add to this equation to create another thing for aluminum to get rid of that dot? Another what? Not another aluminum, because he doesn't want, aluminum won't take that dot. Another oxygen. Watch this, watch this. I'm going to add a brand new oxygen. Now watch, I'm going to go to my tally. Whoops, I'd already drawn 1 oxygen. I messed that up earlier. We'd already drawn 1. Now, how many oxygens have we drawn though? Yeah, there's another one. All right, there's a brand new one. How many dots does an oxygen always start with? 6. Oxygen is in group 16. So anytime we find new oxygen, they always start off looking like that. That's oxygen. Watch. Remember that dot that aluminum was angry about? Aha, I found somewhere for him to go. Hey, what does this aluminum look like after that red happens? Stable, because he is naked. There he is. Another happy atom. Yay! We've got 1 happy atom there, 1 happy atom there. Let's see what this oxygen looks like after the move. What does the oxygen look like? Yeah, he already had 6. All right. Whoops. He already had 6, and then I moved 1 down to there. Is everybody happy? No. Who's angry now? Oxygen's sitting here with only 7 dots. What could we add to the equation to find more dots for oxygen? We're only dealing with aluminums and oxygens. A brand new aluminum. All right. So here we go. Watch. I'm going to introduce a new aluminum. I've now drawn a second aluminum. All right. Hey, look, a new aluminum. How many valence electrons does aluminum always start with? 3, because he's in group 13. 1, 2, 3. All right, let's move some dots again. There's our unhappy oxygen. I'm going to take that electron there. Doesn't matter which one. I'm just picking one. And I'm going to move him to that spot. All right. What does this aluminum look like after that happens? How many valence? Yeah, he's got those 2. All right. 1, 2. All right. What does this oxygen look like now? An octet. He's got 8 now. 1, 2, 3, 4, 5, 6, 7, 8. Hey, check it out. I found another happy guy. There's another happy oxygen. Is everybody happy? Who's not happy? Look at him. 2's no good. It's got to be 0 or 8. What can we introduce to find a place to give those 2 electrons? Let's add another oxygen. There's another oxygen. How many valence electrons does a new oxygen always start with? Always starts with 6, because he's in group 16. All right. Let's move some dots. That one is going to go to there. This one can go to there. When that happens, this aluminum is now naked and stable. This oxygen is now surrounded by an octet, which means I have discovered another 2 happy atoms. Is everybody happy? Yes, look, there's no dots. There's no dots hanging out. I've got these 2 happy aluminums. I've got these 3 happy oxygens. Look, look. The only way that aluminum and oxygen can form a compound is like this. Write that down. This is the big moment of the day. The only way that aluminum and oxygen can come together is like this, is if there's 2 aluminums and 3 oxygens. Why? Well, that's why. If you had any different number, there'd be an unhappy element somewhere. There'd be valence electrons that weren't in 0s or 8s. And the whole reason that bonding happens is to make everybody become stable. So you can never have Al2O2. No, that doesn't happen. You can never just have ALO. You can't say, oh, well, if aluminum and oxygen get together, it's ALO. No, it's Al2O3, because that's the only way this will work. Now, for those of y'all thinking to yourself, holy crap, that was a lot of work. That's what tomorrow is for me to show you that it's not a lot of work. You want to see my secret? You said you want to see my secret, right? Here's the secret. Put your finger on aluminum. If you run your finger to the very top, what is aluminum's predicted charge? It's +3. Put your finger on oxygen. If you run your finger all the way to the top of oxygen, what is it? -2. Does everybody see the -2? What we're going to be doing all day tomorrow is called the crisscross. Because if I take this and assign it as his number, and I take this and assign it as his number, it'll become this every single time, no matter what 2 elements you're mixing together, bonding together, rather. The crisscross does all the dot moving for you, but it takes some serious practice to learn all the rules that come with that awesome, amazing shortcut.